Hello, welcome to this short video on induction. This is an introductory lecture on induction. What is induction? It is a powerful method for showing a property is true for all non-negative integers. So we have to describe the problem in terms of some kind of a non-negative integers. In other words, we have to enumerate the problem using non-negative integers. Induction plays a central role in discrete mathematics and computer science, and in fact, its use is a defining characteristics of discrete as opposed to continuous mathematics. We'll discuss two versions of induction in this course, ordinary and strong. We will only focus on ordinary induction, which some people call as weak induction, in this video. We will also explain why induction work and how to use them in proofs. It also introduces the invariant principle, which we will learn later in the semester, which is a version of induction specially adapted for reasoning about the correctness of programs. In brief, induction is a powerful proof technique for proving things about problems that can be enumerated using a sequence such as 1, 2, 3, 4, 5. What is our intuition for induction? What is real induction and how does it really work? Let's assume that there's a basket of candy that is numbered from 1, 2, 3, etc. And let's assume that there's a number of children are lined up to receive candy. And we can name these children as 1, 2, 3, and so on. And then we have the nth child in general, and then the n plus 1 child is the next child. So we are going to introduce two rules. The rule number 1 is the first child always gets a candy. The rule number 2 is if the child n gets a candy for any n, then the child n plus 1 also gets a candy. That's rule number 2. So this is rule 1, and this is rule 2. And it's not hard to reason the following fact. Rule 1 says child 1 gets a candy, therefore child 2 must get a candy. If child 2 gets a candy, then the child 3 gets a candy, and so on. So therefore we can show that it's true for any child number, regardless of the number, provided that you have a candy basket that never runs out. More formally, the principle of induction always involves a predicate Pn, and the inductive specification is one of the things you have to prove, that your Pn implies, or we call it inductive hypothesis, that Pn implies Pn plus 1. And we have to show P naught is true, or P1 is true, or P2 is true. Wherever you want to start, that's fine. It doesn't have to be 0. And then by using that, if you can prove these two rules are true for a given predicate, Pn, then we know the predicate is true for all the integers m. That's the goal. So let's take a look at a proof. We want to show that 2 to the n is greater than n for all n greater than or equal to 1. We have an intuition that this must be true, because we know that if you draw the graph, 2 to the n is an exponential function, and that's going to be, so we are only doing it for n greater than or equal to 1, so it'll be something like this. That would be 2 to the n. And the function n is a linear function, and you can see that 2 to the n is always greater than n. But we must prove this. Proving by a graph or picture is not enough. So let's assume that our predicate is 2n is greater than n. Now we want to show a few things. First of all, we want to show that P1 is true, because notice that we are starting from 1. So P1 says 2 to the 1 is greater than 1, which we know to be true. So then let's suppose Pn is true. So this means that we know that 2n is greater than n. So now we want to show Pn plus 1 is true. So how do we show that? Let's suppose that we write Pn plus 1 means 2n plus 1. We know 2n plus 1 is equal to 2 to the n times 2. And because from the induction assumption that, or hypothesis, we know that 2n is greater than n, we know then this has to be 2n is greater than n, so therefore this has to be greater than n times 2, because 2n is greater than n. So this means that we have this is equal to 2n, and it's not hard to see that this is greater than n plus 1. Because if n is greater than 1, 2n has to be greater than n plus 1. You can simply see that by taking the n to the left-hand side. And therefore, we establish the fact that 2n plus 1 is greater than n plus 1. This means that Pn plus 1 is true. And therefore, by induction, this proposition is true for all n greater than or equal to 1. So let's want to prove here next that fn equals 2n minus n is a strictly increasing function. So how does the proof goes? To show that fn is strictly increasing, we need to show that if x is greater than y, then fx is greater than fy. Because our domain is n, we can just show that f of n plus 1 is greater than f of n for all n. That is, we want to show that this fact is true. That means 2n plus 1 minus n plus 1 is greater than 2n minus n. But we know 2n is greater than n from the induction that we did in the previous problem. And therefore, if you multiply 2n plus this from by 2, we can show that 2n plus 1 is greater than n plus 1. Hence, by subtracting, we get 2n plus 1 minus n plus 1 is greater than 2n minus n. Therefore, we show that fn plus 1 is greater than fn. This means that f is a strictly increasing function. Induction and recursion. Is there a connection between induction and recursion? In induction, we prove that the base case, which is either phi0 or p1 or some base case. Then we prove that if Pn is true, then it implies Pn plus 1 is true. In recursion, we have a base case, then we explain the Pn plus 1 in terms of Pn or lesser terms. So another way to explain is that the recursion is a programming strategy for solving large problems, sort of like divide and conquer, solve the large problems by splitting into small problems of some kind. Induction is a mathematical strategy for proving statements about these large sets of things. So they are kind of related, they look very similar, but they are doing two different things. Recursion is an algorithmic technique, and induction is a proof technique, and they are both very useful in computer science. So what are the key steps to an inductive proof? So the key steps are: step 1, we have to state that the proof is done using induction. In other words, we say something like, we prove this statement by induction. Next, you have to define a proposition, Pn. For example, you can say the proposition Pn is that the n is greater than square root of n, something like that, right? For n greater than or equal to 2. Step 3 is that we have to show P0 or some base case is true. So in this case, we're going to show that P1 is true because we can just easily see that 2 is bigger than square root of 2. Suppose Pn is true and we want to deduce Pn plus 1 is true. In other words, if n is greater than square root of n, then we want to show that n plus 1 is greater than square root of n plus 1. Now we're not proving it here, but we are specifying the steps that are needed for an inductive proof. Finally, step 5 is to conclude that Pn is true for all n. So let's go through this one more time. Step 1 is to state that you're going to prove something by induction. Step 2 is to define the proposition that you're going to prove. Step 3 is to prove a base case, which is usually very simple. Step 4 is the harder part, that you have to show by assuming Pn, you can deduce Pn plus 1. And then we finally conclude. We write one statement that says, because step 4 is true, we can conclude that Pn is true for all n. So here are some interesting examples about properties of summations that we can prove by induction. This is the sum of all the n integers from 1 to n, which is given by n times n plus 1 over 2. This is the sum of the squares of the integers, that's 1 squared plus 2 squared and so on. This is the sum of the cubes of all the integers from 1 to n, that's 1 cubed plus 2 cubed plus 3 cubed and so on. All three facts can be proved easily by using induction. So let's take one of these things and try to prove it by induction to understand how the induction might work. So here's the proof. We want to try to show that the sum of all the squares from 1 to n is n times n plus 1 times 2n plus 1 over 6. So we prove this by induction. This is how we have to show that this is our intent to prove it by induction. Then we state the proposition. Our proposition is summation k squared from 1 to n is n times n plus 1, 2n plus 1 over 6. So this is our base case where we prove. So our base case is that P1 is the left-hand side. So if you assume that n equals 1, then we show that if you plug in n equals 1, that means you just have one term here. So your left-hand side is just 1 squared, that's 1. And the right-hand side, you just plug in n equals 1, and you get this, which is also equal to 1. Therefore, left-hand side is equal to the right-hand side. So we know that P1 is true. So the next step is we assume that Pn is true. That means we know, or we assume, that k equals 1 to n, k squared, is n times n plus 1 times 2n plus 1 over 6. So now let's look at the proposition Pn plus 1. That proposition is the summation k from 1 to n plus 1, k squared. Now in this case, it's not hard to know that this summation can be broken into two pieces, k from 1 to n, k squared, and then the n plus 1th term, which is n plus 1 squared. So by induction, we know that this summation is given by here. So therefore, instead of this, we can replace the formula based on our induction hypothesis. And on this side, we have n plus 1 squared. Now the key is, what are we trying to show? What we are trying to show is that Pn plus 1 is true. That means if you replace n by n plus 1 here, or get n plus 1, n plus 2, then 2 times n plus 1 over 6, we're going to be all good. Now one thing we notice is that the n plus 1 is common to both sides. So we will take n plus 1 out, and also we will take 6 out. If you do that, then you will have n times 2n plus 1. That's from this side. And then you will have 6 times n plus 1. This is a little bit of algebra that you have to do to get there. And then we write n plus 1 over 6 times, and if you simplify this, you will get 2n squared, plus you will have n plus 6n, that would be 7n, plus then you have a 6 in here. So now if we can show that this is in fact n plus 1, and if we can show that this is n plus 2, and this is 2n plus 3, if you factor this part here, then I think we are all set. Because what that means is that if you take this and replace n by n plus 1, then you get the following: n plus 1, and then 2 times n plus 1, and divided by 6, which is exactly n plus 1, n plus 2, and 2n plus 3. And so we have to convince that this factorization of 2n squared plus 7n plus 6 is in fact n plus 2, 2n plus 3. see whether that's the case. If you multiply that's 2n squared, 4n plus 3n, that's 7n, and then 2 times 3 is 6. And therefore we prove the Pn plus 1. Hence, this is true for every n. And that's your proof by induction. Here's a faulty induction proof. The faulty induction proves that every set of n dogs are the same color. So let Pn be the proposition that all sets of n dogs are the same color. Then P1 is obviously true because you have a set of one dog and that dog has to be the same color. Assume Pn is true for some n greater than or equal to 1. This means all sets of n dogs are the same color. So let's consider a set of n plus 1 dogs. We name them from d1 to dn plus 1. By induction assumption, the last n dogs have to be the same color because our assumption is that any set of n dogs is the same color. Also, the first set of n dogs are the same color, d1 through dn are the same color by induction. This implies that all n plus 1 dogs are the same color, because this means that both colors d1 and dn plus 1 are the same. So where's the fault in the proof? The fault in the proof lies in the fact that we are proving really P2 implies P3, and P3 implies P4, and so on. But we never prove that we can go from one dog to two dogs and prove that two dogs are the same color. But if you tell me that any set of two dogs are the same color, then I can show that any set of three dogs are the same color. If you show me three dogs are the same color, then I can show that any set of four dogs are the same color. So this is an example where the induction fails because we did not check whether our assumption about how we argue that any set of n plus n dogs is the same color implies any set of n plus 1 dogs are the same color is actually false. So that's a faulty induction proof because one of the things we assume that P1 implies P2 actually fails. So let's do a workshop. We want to prove that 3 is a factor of n cubed plus 2n. So how do we show this? So let's go through the proof here. So we say the proof by induction. So let's prove the base case. So our Pn, our proposition Pn, we have to state that, says that n cubed plus 2n for any n is a factor, 3 is a factor of that. In other words, it's 3 times some other integer. In other words, 3 divides n cubed plus 2n. That's another way to say that. So base case is, let's take a look at P0. If you want P0 or P1, it doesn't matter in this case. P0 is that 0 is 3 times some integer x, which is true because we could choose k to be 0. So let's assume that Pn is true. Pn is true. This implies that n cubed plus 2n is equal to 3k for some k. Now let's consider Pn plus 1. This means we want to look at the expression n plus 1 cubed plus 2 times n plus 1. Let's simplify and show that this is also a multiple of 3. So if you factor this out, you will get n cubed plus 3n squared plus 3n plus 1, plus then we expand this, that would be 2n plus 2. So this gives us n cubed plus, I'm going to include a 2n here, n cubed plus 2n, so I'm going to take these two terms, and then I'm going to gather the other terms. So the other terms are 3n squared, so I'm going to factor out 3. So 3 times, let's do n squared here, and then this is going to be n is 3, and then 1 plus 2 is 3, so that would be 1. So this means we know that this is, by induction assumption, we can call this some 3 times k, and then we can call this some other number. Let's call this m or something, so that would be 3 times m. So this implies that it is 3 times k plus m, or if you replace k plus m by p, then we show that it's 3 times p for some p. So this means that our proposition for n plus 1 is also true, because Pn plus 1 says n plus 1 cubed plus 2 times n plus 1 is a multiple of 3. So this is an example of proof by induction of something that could be hard to do by other means. We'll talk more about induction in our video on strong induction.